Ready to go? It's like real school now, right? Taking notes, getting a lesson. But here's the thing, I am left-handed, and it takes me a little bit to get back in the swing of writing on this tablet, and not having my hand mess it up. So I'll try and be as neat as I possibly can. Today we're talking about real numbers and their properties. I guess I didn't have to capitalize that T. Right. So everything that we are going to talk about today is a real number, right? It's the only thing we're dealing with. We're not moving into the imaginary numbers or the complex number system. Real numbers defined are made up of two different categories. Look, I forgot where I'm supposed to capitalize stuff and not now. The first category we've got is the irrationals. Right. An irrational number are numbers where their decimal form does not terminate. Can anyone think of an example of a number where the decimal form doesn't terminate? It goes on forever and ever. There's a super obvious one. At least I hope it's super obvious.
Pi.
Pi. Yeah, pi goes on forever. It's a decimal that goes on forever. Square root of 2. Square root of 5. Heck, square root of 7. Clearly, it's not true of all square roots. Like the square root of 49 gives you a nice whole number, so that decimal will terminate, right? But if the decimals don't terminate, then they are irrational numbers. The rest of our real numbers would be rational. If these are irrational, the other ones are rational. And the rational numbers, by definition, are the opposite, right? They're numbers where the decimal form does terminate or repeat. Terminate. I am a math teacher, not an English teacher, so spelling is not my terminates or repeats. So if you see something that says like 0.06 with a line over it, that means that 6 is going to repeat forever and ever and ever. So that would be a rational number, right? 5 is a rational number. The square root of 49 is a rational number, right? Because it just equals 7. So pretty much all other numbers that are real are going to be rational. But the rational numbers have subcategories. Very exciting stuff. And we'll talk a lot about the subcategories today, and then we will never talk about them again. Also, rational numbers, the reason they're called rational is because we can write them in the form of a fraction, right? So we have the subcategories which would be the natural numbers, that we refer to as n, or sometimes you'll see it with an extra line in it, n. And what the natural numbers are they're all your counting numbers starting with the number 1. 1, 2, 3, 4, forever and ever, right? Your next category, your subcategory, would be the whole numbers. And we call the whole numbers W, and sometimes you will see that also. Oop, told you I can't write today. Call that W. And you'll also see it represented a lot with an extra line in the W. It's just a way of labeling sets. For some reason, they put an extra line in. The whole numbers are the exact same thing as the natural numbers. The only difference is we start counting with 0 instead of 1. Notice we're only dealing with positive numbers when we talk about the natural numbers and the whole numbers. We're not moving into negatives. Negatives come in the next category, which is integers. Now, if natural numbers are represented by the letter N and the whole numbers are represented by the letter W, what would you suppose integers are represented by? You would think, right? That seems like the obvious choice. But no, mathematicians are stupid. So they went with the letter Z. Now, I know why they didn't choose I, because I is what they use for the irrational numbers. I have no idea why they chose Z. But they did, and it represents all of the whole counting numbers, but it also includes the negatives. So if I have like -2, -1, 0, 1, 2, all the way to infinity. So we've got infinity in both directions when we're talking about integers. The rational numbers are represented by the letter Q, not the letter R. And the reason for that is that R is used for the real number system to represent real numbers. Rational numbers are fractions. And fractions are division. And Q stands for quotient, right? Quotient's always associated with division. I don't know if you know this about rational numbers, but all rational numbers can be written in the form of a fraction. So if I have 3/4, that 3/4 means 3 divided by 4. And that division symbol is just representing the fraction without knowing what the numbers are, right? This line right here in a division symbol or in a fraction just means divided by. Right? Mind blowing. Just changed elementary school for you right there. So when we categorize these, if you notice, we've got 1, 2, 3, 4. Well, the only thing different with the whole numbers is it starts with 0, and then the integers start with the negatives, right? But each of these subsets fits into the next set. And what I mean by that is the natural numbers, smallest subset, right? Just above that, having only one more number than the natural numbers is our whole numbers. It includes all the natural numbers plus 0, right? Our next set is the integers. We've got Z. It includes all of the whole numbers and all of the natural numbers. Our next set includes, I love it when it makes the circle perfect for me. The next set includes our rational numbers, right? So all of these sets are part of the rational numbers, right? They're all little subsets. Each set fits in to the next set. And all of these are part of the real number system, right? They all fit under this big blanket category called real numbers, which is represented as R. The irrational numbers are part of the real number system, and they're called I. Right? So they're all real numbers, but most of them fit under this set of rational. And then you've got your irrationals on the side. So we're going to do like a couple of examples of all of them because, that's what your homework does. So on your homework problems, for those who haven't gotten to it yet, you're going to be given like a problem. It's going to say 1 is -10. And then you are going to have to list all of the groups that this belongs to. Well, -10, it's not a natural number because it's negative. It's not a whole number because it's negative, but it is an integer, right? Which means it is also a rational. And if you want to go as far as to say it's real, it is real. I always take real as a given. If you don't enter the real part of it, all we're dealing with right now is real numbers. You might get something like, okay, I like problems like this. What if you have 24/8? This is a fraction, right? Simplify it first. 24 divided by 8 is just 3. Where does 3 fit in? 3 fits into everything but irrational, right? It's a whole number. It's a natural number. It's a whole number. It is an integer. It is rational. And it is real. Make some sense? You'll get tricky questions like pi minus pi. Pi in and of itself is an irrational number, but pi minus pi just equals 0. And so 0 would be whole, it would be an integer, it would be rational, and it would be real. Make some sense? So some of them will get a little tricky on you, but most of them are good. So just make sure you reduce these problems a little bit, like negative square root of 81. Well, that's just -9. And so you'd go, well, where does -9 fit into all of this? So that is all I have in terms of that. We're going to move on to properties. Properties, you don't ever have to really memorize the properties of numbers, but it helps to understand how they work. And when I do properties, I like to break them up into, look at that, I keep making that bigger with my hand. Bigger or smaller. So when I talk about properties of numbers, of real numbers, I should say, I like to go with the property. And then I like to give you an example of the addition and an example of multiplication, because it should work a little differently with both. Notice we don't ever talk about examples of subtraction or division. And the reason for that is subtraction is just addition, right? It's adding negative numbers. Multiplication and division are the same, right? They're just inverses of each other. Division is the opposite of multiplication. So if something applies under division or it applies under multiplication, it automatically does with subtraction and division. So the first property we are going to talk about here is the commutative property. In addition, it says if A plus B, if I have A plus B, it's going to equal B plus A, right? They're going to have the same solution. In multiplication, it's saying A times B equals B times A. And if you think about that, you could see that it's true. If I made A3 and B2, that's going to be the same as 2 plus 3, right? 3 plus 2 and 2 plus 3 are both going to equal 5. Same here if I made A3 and B2. And right, 3 times 2 is 6 and 2 times 3 is 6. So you can see how that works, right? It just means it works in any order. Commutative deals with order. The associative property deals with groupings. So the associative property says if I have A plus B plus C, if I have these two grouped together, it's going to be equal to if I had these two grouped together. It's saying that how I group them, as long as they're all addition, does not matter. And like I said, I don't care if you down the road remember the names of these. I just need you to understand how they work. And it's going to work the same here. If I have A times B times C and these two are grouped together, I'm going to get the same solution if I have A times B times C and those two are grouped together. It's not going to change the value, right? If I put in numbers for A, B, and C and I group them differently, I'm going to get the same solution either way. Our next property is the identity property. And identity is pretty easy to remember if you think of identity as self, right? The identity property is what do we do to something to take it back to itself. So if I have A plus something and I need it to get back to A, I have to think about, well, what do I add to A to get A back? And there's really only one thing you can add to it to make sure you get itself back. Does anyone know what that is? Did you guys hear my neck crack when I did that? Well, if I add A to A, imagine A is a number. Imagine A is 2, right? What would I add to 2? Yeah, exactly. It's always easier to figure these things out when you replace it with an actual number in your head. So if I add 0 to something, it's not going to change the value of it. When I'm multiplying, if I'm going to multiply something and I need to get A back, what's the one thing I can multiply by to get that same number back? So 2 times what? Exactly. 2 times 1. So our identity gets it back to itself. So when we're talking about addition, we would add 0 to something to get it back. When we're talking about multiplication, we'd multiply that times 1. Inverse with addition, we're trying to get to 0. So if I had A plus something and I want it to equal 0, I would have to think about, well, what am I going to add to A to get 0? When I'm talking about multiplication, I'm going, what do I have to multiply times A to get 1? So when you're talking about that, what would you multiply to A to bring it back to 0? This one's getting a little harder. And nobody wants to take a shot at this one, huh? This is where we're bringing the negative numbers in. Remember when I said that addition and subtraction are the same thing? We're just adding negative numbers, and that's what subtraction is. So if I have A and I need to get 0, I would just add negative A, right? So if I have 1 and I need it to equal 0, I need to add something to it to equal 0, I would add negative 1. If I have A and I need to multiply something times it to get 1, in the same respect, I would multiply it times 1 over A, right? Because if you think about that, that would give me, if I have A times 1 over A, that would give me A over A, and anything over itself just equals 1. I'm going to take a tiny break here for a second. So just be patient with me. I have to answer a question really quick.
Sorry, I didn't mean to interrupt.
That's all right.
Is your son a Padres fan?
Huge.
Backpack.
Oh,
We went to the game on Saturday.
he's going to love that.
Saturday. It's all his.
Thank you so much. That's
You're
awesome.
welcome.
Thank you.
Yeah, I saw that on Facebook.
He is a monstrous Padres
Okay.
fan. Sorry about that. Mrs. Kingsburg just brought my son a Padres backpack. We're huge Padres fans. I probably just turned half of you into enemies, but the last property that we're dealing with here is the distributive property. And you guys have used the distributive property a lot in Algebra 1. I don't ever write the distributive property under addition or multiplication. I kind of put it in the middle because it uses both. So if I have A times B plus C, it's going to equal A times B plus A times C. And I'm sure most of you remember that because you used it to FOIL a lot down the road. Back when you guys did Algebra 1, maybe used it a little bit in geometry. The next thing you're going to have to do in your homework is you're going to be given problems, and you're just going to have to tell me which property is being used. So if I had 5 times 2 times 8 equals 5 times 2 times 8, you would look at all your properties and you go, oh, well, that one's just associative, right? If you want to be specific, it's multiplication, right? But all I'm asking for is what property is being used. So if I had 7x plus negative 7x, we go, okay, well, what property is that? That would be additive inverse, or you could just call it inverse. That is really all you have to the homework problems. Normally, I'm actually going to stop the recording before I go on to the normally.